So everyone's gone quiet, so I think that's a sign. So welcome everyone. I'm Mark Sefton, Head of Department at present. So it's fantastic to see Stephen elevated to Professor, and we're here tonight to sort of celebrate that and hear about Stephen's journey. But first, I need to mention something in case there's an emergency. I've been told to give a safety briefing. So in the event of a fire, please follow the emergency exit signs and exit the lecture theatre, either in these doors or at the back of the room. So Stephen has had an impressive scientific career, a big chunk of which we're lucky to have benefited from in the department. But he started with a Bachelor of Science from the University of Cape Town in chemical engineering, a PhD from UMIST on modelling flotation froths. He was then a research associate in UMIST and then a lecturer in chemical engineering in the same university. And then he saw the light and came to Imperial College in 2005. He was promoted to reader, and then finally he's reached the current pinnacle of his career as Professor in Minerals Processing here in our department. And Stephen's very impressive. Everything he does is incredibly well done. He has incredible scientific credentials, but I think for his friends and colleagues in the department, the first thing we would say is what a wonderful departmental citizen and generous person he is. So he helps to run our Metals and Energy Finance course, and it's really nice to have his superior intellect training a collection of superior intellects. So we need our lecturing staff to be up here because the students are pretty close to that level as well. And he also helps out in lots of other things, and the department is perpetually grateful for that, Stephen. He's also got other skills. And I'm sure, Stephen, you won't remember this as being one of the highlights of your career, but it's a highlight nonetheless. Your team won the Christmas quiz in the department. And I spoke to Jan after, and I said, how did you manage that? Because Jan had some money in the pot, I think, and he would have lost it if Stephen hadn't helped to win it. And Jan said to me, it's Stephen. He's an absolute quiz genius. He's an absolute ringer. And he said he's the best guesser in the business. I think that's a compliment. Stephen has this incredibly impressive list of publications. His peer-reviewed publications are very strong, and they all speak to his experience and expertise in mineral processing, in particular froth flotation and heap leaching. And to prove that he's an intelligent individual, he actually avoids the dirty work by spending most of his time in front of the computer modelling these things and leaves it to others to actually do the experiments themselves. So Stephen's future plans appear quite modest, simply to supply the world with raw materials it needs to prosper in the future. And we'll all remember Stephen's work in the department, because every time we see percolating water or froth in Starbucks or Costa Coffee, we always think of Stephen and the sort of work that he does. So, thanks, Stephen, for being a wonderful member of the department. We're all really looking forward to your talk, and your talk is modelling and measuring minerals processes.
Thank you. Well, thank you, Mark, for the very kind introduction. So before I get on to the actual talk, I'd like to acknowledge all the people that I've been working with over the years. So the talk today will cover some work I've been doing over the last 20-odd years, and so I've worked with a very large number of people over that time. And so these are some of the people who have particularly contributed to what I will be presenting today in terms of the work I'm going to be giving. Okay, so my talk is on modelling and measuring minerals processing, and that's pretty much what I've been doing, particularly focused on the modelling side. I like designing experiments, but tend to not run experiments. So most of my work is actually on the modelling side of this. And I suppose the first question is, why do we want to study and model minerals processing systems? From my perspective, of course, it's because they're really interesting and challenging problems to actually tackle. But I don't think Mark wants us to just study things that are fun and interesting. There must be somebody willing to sponsor this work. And so the main reason that minerals processing is such a hot topic, I suppose, in terms of the challenges in it, is because of, first of all, the massive increase in the demand for metals over the last number of years. I'm using copper as an example, and approximately 90% of all the copper ever mined was mined in the last 100 years. And to put that into perspective, in the 18th and 19th century, the UK was the biggest producer of copper in the world, and at its height, it was producing about 75,000 tons of copper per year. These days, there's a single mine in Chile, admittedly the world's biggest copper mine, Escondida, that is producing 1.2 million tons of copper per year. So just that out of a single mine. And it's not just the amount of copper or any of the base metals that is being produced that is increasing. It's also becoming more challenging to extract those materials. The grade of the ore that is being fed into these mines is continuously dropping. The average grades 100 years ago for copper were maybe about 2.5%. At the moment, they're less than 0.5%. So 99.5% of the stuff you're putting into these processing plants is junk. So there's a big challenge in being able to extract that. And 100 years ago, the grades were even higher. UK copper grades were maybe 15% in terms of what was being mined. That means you could dig the stuff out of the ground and smelt it pretty much straight away. About the only minerals processing that was carried out in that era was actually hand sorting. So there'd be people at the end of the production thing knowing what waste rock looks like and pulling pieces of waste rock out of the feed to the material. And for copper, this actually presented a really big challenge maybe 120 years ago. They were getting to the point where these sorts of really high-grade deposits were dropping, knew about large deposits but at much lower grades. But the problem with copper ores is they're not much denser than the gangue that they're in, so the waste rock that they're in. So there's a real challenge in density separating for copper, which was about the only technology available at that time. But luckily, about 100 years ago, a new technology came along, which actually effectively saved the copper industry and allowed material to actually be separated at these much lower grades. So you need to get your material from these days, 0.5% that is coming in, up to maybe 20 or even 30% to feed it into the smelters. And froth flotation can do this for you. So froth flotation is a way of separating minerals you want from the minerals you don't want, and do it based on hydrophobicity. So you basically do it based on how water wetting the particles are. So if you have some particles that are hydrophilic, so want to stay within a water phase, and other particles that are hydrophobic, so don't like to be water wet, if you bubble air through a mixture of those, the particles that are hydrophobic will stick to the air bubbles, and the particles that are hydrophilic won't stick to the air bubbles, and so you can carry the particles you want to the surface of the froth and therefore recover them. Of course, most minerals out there, including the copper minerals, are actually naturally hydrophilic, so they naturally wouldn't float if you bubbled air through them, but you can add surfactants. So you're basically adding chemicals, and these chemicals that you add will selectively attach to the minerals you want. So they'll absorb onto the surface of the minerals you want and will turn them from being hydrophobic into hydrophilic minerals. So the flotation process itself occurs conventionally in a flotation cell, and these flotation cells have two parts to them. They have the bottom section, which is mixed. You have an impeller at the bottom, so very rapidly spinning impeller, and it's actually along the shaft of that impeller that you're introducing the air. So the air comes down that shaft, gets broken up into fine bubbles in the impeller, or between the impeller and stator. And then you have a relatively well-mixed zone at the bottom, which is where all your particles that you want end up becoming attached to the surface of these bubbles. These, of course, then rise up to the surface of the froth, of the surface of the cell, and form a froth layer at the top. And this froth is actually very important for the performance of the cell, and we'll get to that in a minute. But this froth then overflows, and that is what is actually collected as your concentrate, so collected as the product from these cells, whereas the material that flows out to the bottom of these cells hopefully contains substantially less of the material you want, and so that is the tailings or waste stream from the cell. And these cells work in series. Each one of the cells might only pull out 20% of the material you want, but if you put a whole sequence of them, you'll end up pulling out most of the material you want. So, my work has particularly focused on the froth phase, and that's because it might not sound at first glance that the froth phase is that important a bit of it. It's transporting the particles over the top, but it plays a really, really important role in the purity of the product you get. If you're pulling material out the top of one of these cells, you're pulling water over with the material, so the stuff comes over with water, and the things that are in the water are there non-selectively. This means that the water just pulls over a random selection of what's actually in the pulp, and the problem is the pulp contains 99% stuff you want, and maybe 99% stuff you don't want, and maybe 1% stuff you do want, which means that stuff that's pulled over non-selectively will pretty much all be stuff you don't want. And therefore, the important job of the froth is to reject water. And that's what froths do. As if you've seen any froths, they get drier with height quite rapidly, and so you have a froth that is drier, and so you can pull over a drier froth and therefore pull over a purer product. And that is typically controlled, or it's indirectly controlled, by the size of the bubbles. The bigger the bubbles, the drier the froth, the lower the liquid content, and so the higher the grade you pull over. This, of course, also has the opposite effect on your recovery, because your bubbles, the particles you want, are stuck to the surface of these bubbles, and so as your bubbles grow, you're losing surface area, and so you lose some of the stuff you actually want. So the froths are what control this trade-off between the grade of the material you get and the recovery that you get. And in most minerals processing systems, there tends to be this sort of trade-off between the purity you can achieve and the total recovery you can get. So, first of all, why, therefore, is the pulp phase better understood than the froth phase? And the main reason for that is that you can apply sort of standard chemical engineering type approximations to the pulp phase. At least to a first approximation, you can assume that it's well mixed, which means you can characterize it by a single concentration within it. It also obeys first order kinetics, at least approximately. That means how much material you pull over is proportional to how much is actually in your tank. You double your concentration, you double the rate at which you pull things over. The froth phase, though, can't be predicted quite like that. The bubbles are nearly plug flow, but you then have the water moving. The water moves slower than the bubbles, and then you have the solids moving, and the solids are moving slower on average than the liquid. So you don't have a single residence time or nice single quantities you can use to quantify the behavior of the froth. And so we need to actually go into a bit of understanding of the physics of these systems to understand how to predict them and how to model them. So I'm going to first talk a little bit about the foam structure. So foams, there are three main structural elements you have in a foam. The thing you see most clearly in any foam or froth are the lamellae or films between the bubbles. These films will always meet at the sort of corners, as it were, in sets of 3, and then these corner lines, which are known as plateau borders, will meet in sets of 4 at a junction called a vertex. And these plateau borders have a curvature inward. So if you look at them, they curve inwards, which means that because they've got a surface tension there, the pressure in the bubble will be higher than the pressure in the liquid inside these plateau borders. This means these plateau borders actually exert a suction on the liquid in the films. They actually try and suck the liquid out of the films, and these films only stop thinning when the forces between the two sides of the film are high enough to actually oppose the suction force. In a two-phase foam, so what you get in with beer or a soap foam, this will actually occur at sort of hundreds of nanometers or thinner thicknesses. So these are down around about the wavelength of light thick. And you can tell that because if you look at a soap film, you see all the sort of rainbow colors in it. And that's because of interference patterns in the actual reflections within the films, which mean they are down somewhere around the wavelength of light thick. In our foams in flotation, it's particles that are stabilizing them. So they're probably a bit thicker. They'll be of the size of the particles thick, so maybe in the tens or hundreds of nanometers, tens of hundreds of microns thick rather than in the tens or hundreds of nanometers thickness. But you still have most of your liquid in these plateau borders. And for the modeling perspective, that's therefore important. You can model the liquid flow through these foams as being the liquid flow through a set of these pipes, effectively, that connect, that are fully interconnected through the foam. The other thing you can do is carry out structural simulations of these systems. I'm not going to go into the details of this, but foams are minimum surface area structures. What they try to do, the main energy in them is a surface energy. They try to minimize their surface energy, and so you end up being able to simulate their structure and shape. Problem with this is, of course, you can only simulate maybe 1,000 bubbles in this sort of detail, whereas a flotation froth might contain 1 billion bubbles. So you're many orders of magnitude off being able to directly simulate a flotation froth this way. But there are some useful things we can start to study from this. In flotation, the main way people control flotation cells is to actually look at the top surface. So you have a skilled operator who can look at the top surface of the froth, and knowing from the froth structure and the particle loading on the surface how well the cell is actually operating, and so can adjust the parameters that way. This means that because skilled operators can do it, there's a lot of research into machine vision for doing exactly the same thing. And so it's important to know what is the relationship between what you actually see at the top surface and what's happening underneath. So we do these structural simulations like that. And we can also do them of bursting and coalescing, sort of more unstable froths. But what we're more interested in is actually being able to simulate an entire cell. And for that, we need to go towards a continuum model. So we can't simulate it at the level of individual bubbles. We need to be able to do it at some sort of average level. And so that's what continuum models are about. You take a representative volume of your froth, and you look at the physics going in that, and you try and make a model for that. And therefore, we need for our froth models for 3 different things. We need the models for the gas behavior, we need the model for the liquid behavior, and we need a model for the solid behavior inside our flotation froth. So, in terms of the gas motion, we actually assume that it's incompressible, which might seem a very strange assumption for air, but liquid content of flotation froths are comparatively low, and they flow comparatively slowly, which means that sort of compressible effects actually aren't that important, and including them, that would make the models much, much nastier. We also tend to assume that they're irrotational, which again is a slightly strange one from anybody who knows about rheology. Irrotational implies that, well, typically that's in viscid flow, that you don't have any viscous effects. But we still get quite a good approximation, even though there's very strange rheologies in these systems, and that's because there's a lot of slip at the walls. So these froths actually slip along the walls. They aren't pinned at the walls, and so the internal rheological effects actually don't make a giant difference to the behavior. And so the most important parameters for predicting the gas behavior are the shape of the flotation cell it's actually in and the stability of the bubbles. In particular, how much of the air is bursting at the top surface of the froth relative to how much is actually overflowing. And so we actually characterize this by something called an air recovery, which is just the fraction of air you put into your cell that actually ends up coming over the lip. And you can measure this by image analysis. We can measure, using a camera, the velocity of the froth overflowing. We can have a laser height measurement to measure the depth of the froth flowing over the side of the cell. And we know how long the length of the lip is. So multiply those things together and you get the volumetric flow rate over, and we know how much is going in, or at least if the industry equipment is particularly well calibrated, you know how much is going in. And the thing here is this is not something that was routinely measured in industry before I started doing this modeling and simulation work. We went out to the industry, asked them what these air recovery values are, and nobody had the faintest clue what we were talking about or what we were. So we had to actually develop the techniques for measuring that in the first place. And the thing now, it's actually quite routinely measured by a number of groups, and there's a number of mines on which it's actually being implemented as part of their control strategies. So the point here is that the modeling, it's not just important to actually carry out the modeling itself. The modeling can actually tell you what you need to know. So being able to know what you need to know is just as important as actually carrying out the modeling work afterwards. And while the experimental work isn't stuff I've done, Catherine Hadler and Jan were the ones doing most of this experimental work. When actually going to the plants to measure these air recoveries, it was found that there is a peak in the air recovery. As you increase the air rate, the air recovery increases and then decreases. This wasn't actually expected behavior. It expected sort of either monotonically increase or sort of asymptote to a value, but it does actually go through a maximum on pretty much every plant that it was measured at, and this maximum corresponds to a maximum in performance. So these plants perform the best when they're near this peak in air recovery, and so this has now been used as the basis for a control algorithm for controlling flotation cells in Anglo-platinum mines, and they say that it's led to about a 2% increase in their recovery, which might not sound like a giant amount, but these cells actually operate very well even as they are, so this represents a 15% drop in the metal losses. So this is a lot of extra revenue for them at essentially no extra cost, because this is just a control algorithm. It's not actually any change to their equipment or anything like that. So the next part of what we need to look at is how the liquid moves. So we know how the gas is moving, but we need to predict the liquid motion. And there are three main forces acting on liquid. There's gravity, there's viscous dissipation. So basically your bubbles are moving upwards and your liquid's draining down relative to your bubbles. And so there's a drag force between your liquid and your bubbles. And then there's capillary suction. Basically, I told you about the plateau borders being curved, and so the pressure difference between what's in the bubble and what's in the plateau border. But the smaller the plateau borders are, the bigger this pressure difference. This means that liquid gets sucked from big plateau borders towards little plateau borders, or more, think of it differently, from areas with high liquid content towards areas with low liquid content. And you can combine these three forces to get something known as the foam drainage equation. And this was developed by Dennis and his group in Trinity College, Dublin. And what we did was to solve this liquid drainage equation in a system which is a complex shaped geometry and which is flowing froth. And this is the sort of liquid behavior you get. And the most important feature of this is that when you have a flowing froth, you tend to get boundary layers forming in the system. You have relatively uniform liquid contents internally. In fact, the main thing which changes the liquid content over most of the froth is changes in the bubble size. But near the bottom, so near where the froth and the liquid are meeting, there's a very rapid change in liquid content. And there's also rapid liquid changes in any walls that slope outwards. So you can see another boundary layer against the right-hand wall. And the problem with these boundary layers are they don't change size with the size of the equipment. They're of the capillary length scale thick, whether your equipment is a lab scale piece of equipment, which is what I'm simulating there, or an industrial piece of equipment where you've got like half-meter deep froths. This means that the models as I had for my PhD, where I had a fixed resolution, were relatively simple to solve for lab scale equipment, but become much more computationally expensive for full scale equipment because you would need to put in that lots of resolution at the bottom. But as part of Pablo's PhD, he implemented the same equations in 3D, but in the fluidity framework. So we can now have dynamic remeshing. So basically, the resolution of our meshes follow the features in the froth which are important. So you'll notice here this is just a test case where we're adding pulse of liquid in from the top, and you'll notice the resolution on the right-hand side is actually following where both the gradients and the liquid is moving. So the final thing I needed to add to the models to be able to predict the behavior of a flotation froth is a model for the solid behavior. And there are two main types of solids we need to account for. There are those solids which are attached to the bubbles, and there's hopefully the valuable material, and they'll just move with the bubbles. So you know their velocities, etc., if you know the velocities of the bubbles. The complexity with them is that as you get coalescence and bursting, they become detached. And so you end up effectively dropping particles off the surface of your bubbles and into these plateau borders that you now need to model. You have then these unattached solids, and they enter your froth by entrainment, so they're dragged in by the water, or they come in from this detachment and bursting. And these these solids are strongly influenced by the liquid motion, especially the very particles, they'll just follow the liquid, but the slightly larger particles particularly will have a settling velocity relative to the liquid, and they'll also disperse. So there's various mixing and dispersing mechanisms inside a froth, and that will actually spread things out. And that's actually quite important for flotation. The stuff you don't want will disperse upwards into the froth, so dispersion will cause you to collect stuff you don't want, and at the same time it'll cause the stuff you do want, which has been released higher up in the froth, to disperse out of the froth. So dispersion in general has a bad effect on the performance of your system. And again, it's one of these things which nobody had actually measured. So we needed to consider dispersion, and there's two main dispersion mechanisms in flotation. There's what you might refer to as a plateau border dispersion. You've got these plateau borders which are being dragged upwards by the bubbles. They have liquid draining downwards inside them. So the liquid near the edge of the plateau borders is going upwards relative to the liquid in the middle, which means that a particle near the middle of the plateau border goes downwards relative to a particle near the edge. And this, of course, causes particles to spread out. The other one is a geometric dispersion. These plateau borders form a zigzagging network of channels. So every time they get to a junction, a particle basically has to make a decision as to which way it goes, which causes it to spread out at the same time. And we did because nobody had studied this before, we did some experiments. Well, strictly speaking, a PhD student did some experiments, and I did some analysis of the experiments afterwards. And what we did was we took the foam drainage theory and used it to predict what these dispersion coefficients should look like. And we got a relationship I got the relationship which said that this dispersion coefficient should be proportional to the velocity raised to a power of 1.5. And the experiments, well, actually for once, the real world tended to agree with what the theory said, and we got an experimental value of 1.501, which is pretty close to what the theory actually had predicted. Okay, so we've now put together all of these models. I wrote a simulation code to actually solve them. And so now I needed to look at what we could actually use them for. And about the very first thing I used it to test is actually the effect of the design. There's different ways you can run the froth phase and different designs and inserts you can put into the froth. And so I wanted to test 2 of them. And this is ones which have a ring launder. So ring launders are basically, you have 2 zones to your froth. Each of them, the froth is getting pushed outwards and over into a launder, and then outwards and over into a launder. Or there's what's known as a donut launder. So you have a single launder in the middle of your cell, and the stuff in the middle flows outwards and into it, and the stuff on the outside flows inwards and into it. And we wanted to see if did this make a difference to the performance. And so this is 2 different simulations. So in cross-section, the 2 things they all look the same, but you should remember that this is a cylindrical cell, so these things are getting wider as you head outwards. And you'll notice that there's a distinct difference in the performance of the 2 halves, particularly for the one with that donut launder. The grade being achieved by the inner one, where you're moving outwards, is quite a bit higher than the grade you're getting from the one on the outer bit where you're squeezing the froth inwards. And that's partly, the reason for that is that your froth is actually, as you're going outwards, it's slowing down, moving over a bigger area, and so there's more opportunity for material to drain out of it. If you're pushing it inwards, it's actually having to speed up, and going over a smaller area, so there's actually less chance for material to fall out of the froth. And so we presented this to industry, so actually to Anglo-American, so Anglo-Platinum, and they basically thought that basically a froth is a froth and they all behave the same. And so they actually set out to do some experiments on their cells. So these experiments aren't for the exact conditions we simulated. We presented the simulation for sort of a generic cell, but they went out and actually measured the grades in the 2 halves of their cell with depth. And they did find this distinct difference in the grades between what you have in the inside of the cell and that which you have on the outside, which actually gave them some confidence that our models were actually predicting something sensible that could then be tested in industry. So we've now moved on to, this is the, again, work that Pablo and James have been doing. So this is running the same models but simulating them in 3D with more complicated launder layouts, but the basic equations we're solving are the same, and we're still investigating the same sort of thing. How do these cells perform as you change the design of the inserts inside them? The other thing we were looking at is what happens if you add water to these systems. A lot of the froths are added without water, but these cells work in banks of cells. So what you usually have is a first set of cells which produce a concentrate which isn't quite a high enough grade for you to further process or sell, and you then want to increase the grade up to the point where you actually want to sell them. And these cells, you're less worried about the recovery, you really want the grades to be very high. So the trick that can be done there is to add water to the top of the froth, and therefore hopefully wash out the stuff you don't want out of the froth. So basically replace the water which is entrained with lots of gangue with water that contains no solids. And so we did this on, the Red Dog mine in Alaska, which is a lead zinc mine, asked us to have a look at their system because they were finding that they were recovering far more, particularly silica, than they wanted. And silica was one of the penalty elements they had for the subsequent smelting. So they wanted to get their silica content of their concentrate down. And they were actually considering switching from a submerged header. At the time, they were adding the water into the middle of the froth to whether they should actually be adding the water onto the surface of the froth. And so they wanted to see if we could do some simulations to test the effect of this. And so the first thing we had to do was actually calibrate our models to their existing operations. And I had great difficulties actually trying to do this because I found that I could only get my simulations to match their performance if I either added half as much water as they were actually adding, or I added the water unevenly across the surface of the froth. So if you add water unevenly across the surface, here we're adding it over sort of 2/3 or just over 2/3 of the radius, you end up with this plume of water going up the side. And that plume of water, well, it allows you to recover a little bit more of the valuable material, but these are cleaner cells, you're not that worried about that. The main thing it does is it allows this plume of material you don't want to bypass this water addition and be collected into your concentrate. And firstly, this actually surprised me, but I thought this water that you're adding would spread out more from this initial point, and that's probably the operators thought that that would be the case, but our simulations show that this wasn't the case, that this level of bad addition would cause real problems for your performance. And they actually went and looked at their cells, and they noticed that the ends of their water addition didn't actually go to the edge of the tanks, and that was because the ends had actually been deliberately shortened to aid the putting this wash water header in and out of the cell. If they went very close to the edge, they would get caught up on other equipment, and so they had it in a bit from the edge just for ease of putting it in. So we actually proposed that they do some modifications to this. So Catherine did a lot of the calculations for how you change the holes in the system. And so we modified it. And the modifications literally consisted of making a few of the holes in the wash water addition slightly bigger and adding a couple of plastic T's onto the system to try and even it out. So this just shows our addition. There's some bigger holes right near the end, and there's a couple of T's trying to cover some of the blank area. So very, very simple additions and changes. But when we actually performed tests with these modifications, they found about a 36% drop in the amount of silica they were pulling over. So this had, at the time, about a $1.5 million change in their economic performance. And that's just from drilling a few extra holes and putting in a little bit of extra piping. Of course, came back to the original problem, which is whether you should add the wash water addition on the top. We did those simulations as well. And there we actually found that as they were doing it at the moment was the best thing. The froth actually dries out very rapidly above a water addition point. So you end up with a very dry froth very rapidly above the point at which you're adding water. And so by adding it internally, they're recovering less water and so getting a better performance than if they add it to the surface. And they actually did some experiments after that where they raised their headers and actually operated it as though you were doing surface addition, which is not an ideal way to try and replicate it, but at least it gives some idea. And they indeed found that adding it overhead was not as good as adding it internally. Okay, so on that side, I've now been talking about how you do full simulations of these systems. And the problem with doing the good thing about doing full simulations is you can look at the shape of the cells, you can look at the details of the performance, but the problem with full simulations is that they're sort of like experiments. You're doing a simulation of a single set of conditions, so if you want to find trends, you need to do a whole heap of different simulations to produce a set of trends. And so the other thing I did a lot of work on is trying to produce simplified relationships. So can we actually write out an equation for the performance based on the operating parameters? And the trick there is, can you make enough assumptions that you can actually solve the sets of equations while actually keeping in enough of the physics that the actual things make sense in terms of the behavior? So the first one we did was looking at, can we predict the amount of water we put in? And we had to make some assumptions, such as the liquid content didn't vary in the horizontal direction, it just varied vertically, and that the froth is much deeper than this capillary boundary layer. But once we'd done that, could get some analytical expressions, and these were actually tested on industrial flotation cells by a group in University of Queensland in Australia, and of all the models they tested, ours was actually the one that gave the best predictions of the overall water rate. And that's mainly because the other models that were being tested were typically empirical models. So basically somebody had done a whole heap of experiments, fitted some curve to those experiments, and then tried to predict the behavior of another system. And the problem is a lot of these relationships they hide some of the things that are actually important. So they might measure air rate, and that actually changes bubble size and bursting rate and all these sorts of things. So these predictions often end up bad outside the system they were originally tested for. The other, I've also produced model, not going to go into the details, for the froth recovery, which is the fraction of the material that comes into your froth attached to bubbles, which actually makes it out and over into the concentrate, and the entrainment factor, which is how much, if you have the concentration of your entrained material in the stuff coming into your froth relative to that coming out of the cell at the top. I won't go into the details of that. The other important parameter here is what's coming into your froth, and the bubble size is particularly important. So we've started doing some simulations of bubble production in it, and in a flotation cell, bubbles are actually produced by shear. They're produced by the spinning of these impellers inducing shear and causing the bubbles to be broken up in the shear. And so you need to actually run simulations at the scale of the individual bubbles, which hadn't done before. And the simulation code that I wrote to do this was based on a method called smooth particle hydrodynamics. So this is a meshless way of solving these equations. I don't have a mesh. I have a set of points on which I use it, and it's a Lagrangian method. So basically, the points at which I'm solving it follow the fluid. And the other alternative is the more standard one, which is an Eulerian approach, which is where you have a fixed grid and you work out the velocity of everything on your fixed grid. So I have the points actually following the fluid, and this is ideal for these sorts of problems because things like interfaces are naturally tracked. I don't need to work out how my interface is moving. Because my points of fluid are moving with the fluid, it automatically makes my interface move, and so I can therefore do things like include surface tension, etc. very easily. The very latest simulations I'm doing is actually for a real cell, and these ones are sort of somewhere towards the limit of what I can do. This is sort of hot off the press, it's still running as we speak, and I'm trying to simulate bubble breakup in a real industrial cell. I've got about 17 million SPH particles that you're simulating. I'm trying to get to 10 seconds or so, which is about how long a real cell takes to reach steady state. This is about 1.5 seconds in, which given the time step is about 300,000 time steps already. And this is running on 800 cores and has taken about 10 days to do, which does illustrate the importance of doing these things in parallel. If I'd done this as a serial code, it would have taken about 20 years to do this simulation. Okay, it's taken 10 days, but it's still better than 20 years. So. So this is just showing the same simulations, but slowed down. And looking from the bottom, you can see how the spinning impeller and the stationary stator cause the shear forces which actually cause these bubbles to break up. In fact, some of them don't break up quite there, but it causes the bubbles to become elongated. And as soon as you have an elongated bubble, there's the Rayleigh instability, which will mean they'll sort of pinch off into a set of droplets, which is the same thing you get if you have a water tap. If you turn it on, it'll come down and eventually pinch off into droplets. Same with bubbles. You stretch them out, they'll pinch off into bubbles. So that's been talking all about the work I've been doing on flotation. The problem with flotation is that it has a very fine particle size you need to grind the particles down to actually make it work. You need your particles down round about the size of the mineral grains, which typically means you need them something like 40 to 100 microns is sort of the best range for flotation. And so this requires a vast amount of energy to achieve. It's been estimated that something like 6% of all the world's electricity production goes into comminution. So 6% of all the world's electricity goes into turning big rocks into little rocks. So this is a vast amount of energy going into breaking rocks. For instance, Escondida mine, which is the one I was talking about at the beginning, which is the world's biggest copper mine, the amount of electricity it uses just for comminution, not for anything else on the mine, is about the same as the total amount of energy used by all the households in Glasgow. The total energy is about the same as 600,000 average UK household. So this is an absolutely gigantic amount of energy that is being used. And the other problem, of course, is with the grade. You're milling the stuff which is all of the material. So if your grades halve, the amount of material you need to mill for the same amount of copper doubles. So your energy cost doubles if your grades halve. So there's a real problem here. And there's basically three ways out of this. You can either make comminution more efficient. It's been estimated that in terms of the surface area production, this comminution is only something like 3 to 5% efficient. The rest of the energy goes into heat and noise, basically. And that shows part of the issue. Those are mills from 1942, and they look essentially identical to modern mills. We haven't really changed that much about how milling is done, other than they become much bigger. These ones will be sort of this sort of diameter. Modern ones are 5-meter diameter, but you know, there's some efficiencies in scale, but not giant ones. The other tactic you can do is to pre-concentrate your material. So if you can actually separate the stuff you want from the stuff you don't want at a slightly coarser size to start with, then you don't need to mill the stuff you want, all of the stuff really fine. You only need to mill a part of it, and there's a number of different projects going on that, using various techniques to try to pre-concentrate. And of course, the other tactic is to do something completely different. So we've been doing a bit of work in the milling side, so this is very much a new area working, but again using that same SPH code, but this time coupled to another method called the discrete element method. We can start to simulate what's happening in mills. So here we have about 100,000 steel balls we're simulating, so those are the things that are tumbling, and on the left-hand side without any fluid, and on the right-hand side with fluid. The left-hand side is the sort of simulations that are routinely done by lots of different groups. The big challenge is actually trying to do it with the fluid. The one on the left-hand side took my code about half a day to do. The one on the right-hand side was about 2 weeks. So there's a really big difference between doing it with the fluid and without the fluid. Okay, but let's talk about the other technology. So the alternative to the flotation, or one of the alternatives, is heap leaching. And heap leaching is actually a pretty old technology in its origins. There's something similar to heap leaching was carried out from the 18th century at Rio Tinto mine in Spain. What they did was they took the rock which wasn't of high enough grade for them to treat otherwise, and they piled them into what look basically like rice paddies at the bottom there, so in sets of ponds. And then they pumped water from the river up to the very top and let it percolate through all these, and at the very bottom they put scrap iron in, and the scrap iron would cause the copper to come out of solution, and anything that wasn't would just flow over the back and back into the river. And the reason it worked there, of course, is that the Rio Tinto river contains a lot of ferric ions naturally, so it's naturally leaching of these materials into the river, and it's naturally very low pH. So this is sort of a very natural leaching solution that would work very well. And so it was carried out there. Modern heap leaching, though, only really came into its own from the 1970s, when solvent extraction and electrowinning were done to actually complement it. And it went from very much a niche technology to about 20% of all the world's copper comes from heap leaching now. So heap leaching works by piling up this material into large piles. You can see some of them at the bottom there. So these things can be kilometers long, hundreds of meters wide, tens of meters high. And you just sprinkle acid onto the top of them. So it's nearly like a home irrigation system. The pipes are actually very similar. They're just dripper pipes dripping acid onto the top of this heap. This percolates through the heap, dissolving the copper out. You then have an impermeable layer at the bottom, and that's actually one of the other changes in the way it's operated. Historically, heap leaching had a bit of a bad reputation because of its potential for polluting groundwater, etc. But modern ones have a good impermeable layer at the bottom. You collect the material that comes out, which will hopefully have a lot of copper sulfate in it, and then you recover the copper sulfate as copper via the solvent extraction and electrowinning. So the big advantage of it is that you don't need to mill the ore. The particle size is maybe centimeter size particles. You've just produced them by crushing. You sometimes agglomerate them afterwards, but these are comparatively coarse particles. You don't need to put in a lot of energy into it. They've also got low capital costs. You don't need to build these mills, etc. And you can treat oxides with it. But they have some really serious disadvantages. They only tend to be very good for oxides at the moment, where they can get maybe 70 or 80% of the material of the copper out, which is still quite a bit lower than flotation. Flotation, you might get 85, 90% of your copper out. And for some of the primary sulfides, such as chalcopyrite, which is the dominant copper mineral out there, you'll be lucky to get 50% of your copper out from heap leaching. So there's real problems in the extraction efficiencies, and they have very long times. For the oxides, you might be leaching for 8 to 12 months. For the sulfides, a year to a year and a half. So this is a very long time to wait to get your money back after you've mined the material. In flotation, you've got your money back from it a week later. In heap leaching, you've got it back a year later. So it has these disadvantages. And so we're wanting to really understand the system and try and improve the behavior. And so we looked at it at a few different scales. We're looking at what's happening at the heap scale, what's happening at the particle scale, and what's happening at the sort of liquid flow between the particle scale and what's happening down at the particle scale itself. As I don't have a lot of time for this section, I'm going to be concentrating on what happens at the particle scale. And what we did here was we did a lot of small-scale leaching tests, so where we're trying to keep the water addition on the outside very even, and then we were CT scanning these columns. So we were scanning them to start with every day, then every week, then every month, so we could produce this whole set of images of the rocks, and these were done using micro-CT, so very similar to your conventional medical CT scanner, except you can add much higher energy and much brighter X-rays than you can in those because you haven't got a patient to kill. It doesn't matter what you put into the rocks, don't mind. And because of these higher energies and much smaller samples you're looking at, we get sort of 15 or so micron resolution in this. So we can look in quite detail of what's going on in there. And the challenge then was to actually track this performance. It's all very well just seeing nice images of what's happening. We wanted to actually see what was happening. And so we developed a new algorithm for doing this. First stage was to actually separate all these individual rock particles out, which is nice and easy at the very beginning of your leaching. The problem is as the leaching goes on, various minerals actually start depositing at the points where your rocks touch one another, which actually makes it harder to segment the individual rocks as time goes by because this new added mineral doesn't look that different to the existing mineral. But once we've got it, we could then track the individual fragments, and that was because you needed to track them because as the leaching happens, the rocks settle, they move, etc., so they're not in exactly the same point. And so we need to transform it from what it looked like in its new state to the same one as the original day. And then we could, from that, identify every mineral grain in it and identify the same mineral grain in the first time and what it was like in the later time. So you could tell the change in size of every mineral grain. And this had to be a quick algorithm because we were trying to, in this particular set, we tracked 1.2 million individual grains. So you can produce giant data sets doing this. And this allows us to actually look in detail at what affects the performance. These graphs are showing on the bottom axis the size of the individual grains and on the vertical axis how far from the edge of the rock they are. And as you would expect, small grains leach quicker than big grains, and grains near the surface leach quicker than grains very deep inside the rock, which of course is obvious that that's what happened, but at least we can actually quantify the relative importance of these effects. And they are quite significant. If you look at the bottom there, after nearly 170 days, the stuff near the surface, small grains near the surface, are virtually completely leached, whereas the stuff, large grains in the middle, maybe only 40% of them leached. We could also, because we've got this giant amount of data, look at individual ones of these categories and look at the variability inside them. And so this says something about the variability associated with the mineralogy particularly and the mineral associations. And so you can tell the range of leaching rates. So this is the leaching rate divided by the average for that category. And strange enough, it falls into one relationship over pretty much all the systems, all the categories we measured, which was actually surprising. We'd expect some grain size effect to the relative leach rates. But once we did this, we can get this shape, and this was really important for subsequent simulations because the shape of this dictates how much the leach rate changes with time. If you've got a really wide spread, you've got a lot of very fast leaching stuff and a lot of slow leaching stuff, and of course the fast leaching stuff disappears first. And so the wider your distribution, the more your leaching rate slows down with time. So knowing the shape allowed us to predict the long-term performance. We also carried out simulations at the scale of the individual particles. So this is simulations, but starting with one of these micro-CT images. So we were actually predicting the leaching of these rocks, how the grains are disappearing, and then we could compare them with the real experimental values. And these were calibrated up to 35 days and then predict the long-term behavior. And we can really accurately predict the long-term behavior, which is important because people do a lot of these sorts of leach tests, and it's usually very hard to predict the long-term behavior from the short-term trends, or at least from the macroscopic short-term trends. And so we can do these sorts of experiments in 30 days compared to 6 months or a year you might do for the full leach test. The other thing we looked at is flow through this process. I'm not going to go a lot into the flow, but just show that this is an interesting system, interesting scale to start studying this at. This is simulating water flowing through a set of packed spheres, but in one side, this is through 2 millimeter spheres, and this is through 2 centimeter spheres. And these are both within the sort of range of sizes you get in heap leaching. But at 2 millimeters, you get something which is completely dominated by capillarity. So basically, your flow structure is trying to minimize its surface area. So the shape it forms is to do with surface tension. You still get flow down it through gravity, but the shape of the flow path is capillary dominated. You go up to 2 centimeters, and capillarity still plays a role, but suddenly things are orientating themselves with gravity. So you're getting this change in your flow behavior over the sort of range of particle sizes you get in heap leaching, which of course is a challenge for predicting this, which the industry won't like, but from an academic side, of course, it does make it something interesting to study. And we then also did simulations of the heap itself. So we've incorporated all this into heap scale type simulations to predict overall performance. Okay, so that's what I've done in the minerals processing side, but as part of that, I developed this SPH simulator. So it's because there's so many complicated physics that needs to be included in a minerals processing simulation. Any simulator or general purpose simulator capable of simulating those systems are also capable of simulating a wide range of other systems. So I've been recently, the last few years, working with a number of people on a range of different things. One of them is on tsunamis generated by landslides. So you can get tsunamis generated by either subsea landslides, so where you get flank collapses on a volcano or something like that. You can get a tsunami generated on the surface, or at the one on the top right is for rock falls into dams. So there has been one disaster in the Swiss Alps where there was a rock slide into a dam which swamped the dam wall and actually caused the dam failure. So people are interested in what happens when rock falls occur into dams. So we're simulating that. Another one is on mixing of algae. So algae is grown in raceways. There's a number of people looking at applications for algae. But the problem is you don't want your algae all staying unmixed, because then the algae near the top of the surface will take up all the sunlight and anything lower down will be shadowed. And so they move it around this raceway using a paddle wheel, and this paddle wheel also acts to mix the system up. So I was simulating this mixing process using this SPH technology. Another one is also with solid mechanics, so looking at slope stabilities and how membranes are predicted onto the surface. So the one on the left is just the standard slip circle you get from soil stability. Right-hand one shows an experiment that was done where you packed a container with a lot of soil, put a membrane over the surface, and moved it up towards the vertical, and saw how much the membrane was deflected by the soil into it. And our simulations gave very close agreement to what was actually found experimentally. And the final one I've been working on is simulating rockfall. So rockfall barriers. So you have these cable meshes which are stopping the rocks, on the left-hand side, stopping debris flows down rivers or in river channels, and on the right-hand side, single large rocks falling off cliffs and trying to actually stop them. So I've been doing some work on simulating those, which is quite a long way from minerals processing, but the same code can actually handle these situations as well. Okay, so hopefully I've shown you that the modeling and simulation can play an important role in trying to understand and predict these systems and systems beyond minerals processing. So thank you all very much for your attention.
Steve, thank you very much. That was fantastic. I'd like to, I'm very pleased to be able to give the vote of thanks. So, gosh, it was just fabulous, wasn't it? So I'd like to pick out a couple of things that really stood out to me. And the first one is, what a great introduction to our topic, to the work he does, and to the whole field. Because if you can explain what is a massive area and a hugely complex area, and everything he's done in 20 years with such a delicate introductions we all understood, I think it really takes a very special skill. So that's my first kind of wow of tonight. And the second thing that stood out from a scientific point of view is that if you look at the work Steve does, it's really interesting about the length scale. So he starts every piece of work starting with a millimeter or a micron or a tenth of a micron, or really right down at the tiny bits. And the last things he showed are kilometers big. And so he's working across this 620 orders of magnitude. And that's unusual. It's very unusual in science that people work across such length scales and rather generally stick to maybe a couple of orders of magnitude. So that's quite unusual and quite special. And I think that's really something that stood out for me, that you take it from that small scale to the big scale. And that big scale, of course, leads me to the third thing, which is the industrial application. So I think, again, that's really interesting for me that Steve's a serious scientist. I mean, you can see that here. And his work is incredibly scientific and scientifically rigorous. But at the end of the day, it all goes to industry. And it's industrial application that keeps driving it. And I think that's really impressive and very important in control, in design, in prediction of long-term behavior, in minerals engineering, and then suddenly all these other applications that you go, goodness, he's doing rocks falling down mountains. This is, where does all this come from? How does he manage all of that? So that's incredibly impressive, and those are the key things I wanted to pick out. I want to just tell one tale that we had one of our industrial visitors once, and Steve was doing some work for them, and he showed these models that are so like mind-blowingly complex, and the industrialist said to him, Steve, why do you include everything? Why do you make it so complex? And he said, because I can. And and I want to end with that to say I'd like to thank Steve for all the work he's done for this impressive science, for being part of my team. I really have enjoyed working with you, Steve, and thank you very much. So please thank Steve with me.
Thanks, Jan. Thanks, Stephen. So we've come to the end of the relatively public part of Stephen's evening. After the talk of froth and donuts, his guest will be going for something to eat, no doubt. Their appetites have been sort of prompted by that. So thanks, Stephen, and thanks everyone for setting up tonight to help celebrate Stephen's achievements. Thank you, Stephen.
So when you go